Thank you so much, Parita. Those were some amazing insights on data encryption and OpenSSL. We'll now move into our next talk, which is brought to you by Kushal Pakra on the topic of using the latest TensorFlow features for better skin disease detection. Kushal is an engineer with a passion for data science and artificial intelligence. He is ready to embark on a journey towards a PhD exploring the vast potential of data science and AI. His goal is to contribute significantly to the advancement of knowledge in this transformative field. In this talk, Kushal will explore the cutting-edge features that TensorFlow brings to the table, enhancing the efficiency and user-friendliness of machine learning development. Additionally, we'll take a closer look at a real-world application of TensorFlow through a skin disease detection project aimed at identifying common skin cancers in Australians. Can I please get a round of applause for Kushal?
Thank you so much. So I like the way he read about me more than I actually. Anyway, so let's get started. First of all, thank you for coming here, everyone. I really appreciate your time here, actually. By the looks of the traffic outside, I should really appreciate you guys are here. And so I'm really excited to show you some of my projects that I did. One of them, it's pretty basic, but yeah, we're going to talk about a little bit of ML and DL about TensorFlow and latest features about TensorFlow 2. First thing I would like to ask is, how many of you have heard TensorFlow before this? That's great. And what's the latest feature or latest TensorFlow that you know of? It's currently, as of now. Do any of you guys know? It's 2.13. So that means we've already come a lot further than the TensorFlow that was before. But yeah, so that's the main part of my talk today. Okay, let's start off with this one. Yeah, this one looks better. Okay, so today I'm going to talk about TensorFlow and one of the real-world application of TensorFlow that I did for my own project. Started off as a capstone project before. It's called Skin Diseases in TensorFlow, where we did basically is we detected 7 out of 23 skin diseases that was pretty much common in Australians. One of them was melanoma, actinic keratosis, and much more. So the whole overview is about what is it, what's TensorFlow, key updates about it, application about TensorFlow, how I applied TensorFlow to one of my projects, which was a capstone project. Then it led up to a journal now. And then pretty much a conclusion about TensorFlow itself and the skin diseases, pretty much sites and insights about what it is. So what is TensorFlow? TensorFlow, as you all know, most of you raise your hands so you know, it's an open sourced machine learning framework that was developed by Google. So it's like a toolbox, right? It's like a toolbox where you can pretty much do and you have systems learn from data. Data can be anything. Data can be images, videos, even samples of your voices or anything, but it can actually learn and do things for you. Like thinking of it as a superhero tool in the world of deep learning. So the latest TensorFlow version as of now, I'm speaking right now, is 2.13.0 with key updates. Obviously, every version will have a little bit of updates, but moreover, after 2, there was a significant upgrade when TensorFlow 2 got released, and pretty much had a lot of updates such as improved performance, faster model deployment through Keras serving, or even you can have Hugging Face or other integrations that you can do to deploy your models. Also, pretty much updated pre-trained models and data sets. So basically, you can also actually have a lot of data sets available through TensorFlow platform. And number 3 is higher enhanced Keras integration. So Kera already comes with TensorFlow, and it's actually hand-to-hand like a big small brother for TensorFlow to do things for you. But in 2.13.0, it's actually come as Keras serving, where you can pretty much deploy your pre-trained models, or even you can try to use it as different parts of the model. Like you can have one stock of model which does one thing, and then one stock of model which does another thing, and pretty much mix it if you want to, like multimodal approach, right? So highlights would be eager execution. If you know eager execution, or before the eager execution means is like when we consider artificial neural networks, we consider it as like a black box. We didn't used to know how it worked, what were the circumstantial parameters, how it actually did gave the outcomes, or how it worked. So eager execution basically gives us an insight on actually stopping and halting and adding up all the convolution layers and we can predict where it went wrong with our predictions. So eager execution helps in terms of like basically getting rid of bugs technically. And improved performance, I already told you, faster training and execution before the training. So if you have actually trained any simple artificial neural network through TensorFlow or any other frameworks, you know how the training works and how much time it takes. The longer you have, the bigger the data is, the bigger the number of epochs and the hyperparameter is, it takes a long time to train. It takes ages sometimes. But now they basically did a sort of thing where you can actually train models faster than before. And also Keras integration, which is pretty much one of the, what do you call that? It's called, it's like one of the best features for TensorFlow right now. So I'll move on to application. This is basically an application about skin diseases and skin cancer, like I said. Skin cancer being a major health concern in Australians, especially because of the climate, especially because of the harsh sun that we have here. And also, 1 in 3 Australians is diagnosed with skin diseases, like not skin cancer, but skin diseases, which potentially troubles you. And the way you look or something, and if it's bad if it comes in the face, you know, like, so yeah. And our model basically what it did was we choose whatever the images, basically we had to choose whatever the images publicly available. We didn't have money to buy anything. So we basically found out that our data set called HAM 10,000 had 7 classifications of diseases, of those 7 cancers. We took that and pretty much predefined our, we actually used DALI to even train the model to how it looks like, and the images, how it needs to be produced, so that we can take that and furthermore use it for our training images. So pretty much mix and match of different models to collaborate a single task. So for example, like if you have lack of data set, what are you going to do? So for example, if you're working on skin diseases and let's say you don't have your got a free data set, but it's not good enough. What are you going to do? So nowadays, you have the capacity to actually feed the model with certain images, certain type of images that you have, which was perfect, the HAM dataset images. And then pretty much for training, we actually did make our own images to train it. And then after that testing, we had good results, obviously, so which I'm going to explain that further. Moving on. So this was actually our approach for this project, and this is just on the right side, it's a stat. So our approach follows a best AI practice for starting a small training data set of 460 images. And that was altogether data that we trained the model to. And out of 460 images, we had 30 images that we put it as like an extra, where if there's anything goes wrong, we still have like 30 high quality images that we have so that we can train later. So 460 images gave us about 40% of accuracy to start with. That's basically taking into consideration that it was an unsupervised model, right? Also, the accuracy progressively increased by delta. So have you heard about delta in testing? Anybody has done like model testing and have actually has knowledge about delta? So delta, anybody? So delta is basically the difference between the model that it learned before and the model that it learns after. So it's just exactly. So it's like the difference, we basically tell it as a percentage, right? But then it's a difference of the weights of the model that was before and it was trained after. So we just calculate so that how much delta it is actually increasing. It's just like a parameter for you to say how good is my model or how did it well perform. And each model was actually, we had an average of 1.4 delta, which means is that the model before and the model after was learning 1.4% more and giving us better results than each one. So the reason why this project is very promising is because of the same reason, is we have very short images. If you go on to different, so not now, but obviously if you go on to do autoencoder unsupervised classification, you'll have models that takes a lot of images than we have. It's about like we took about 2 to 4% of the images that was actually being used for other models to be. And what our catch is basically we give a learning curve to the model and pretty much start feeding images up to. So we did a 40% accuracy. Now actually it's a journal. I'm continuing this project still, and it's a journal, and we have 75% accuracy right now. So the journal is on a conference happening on November. Pretty much if I'm able to, I can also pretty much come up for another conference for about the same thing. We can actually relate that with this talk as well. So these outcomes basically were accomplished with autoencoder and the 7-class classification algorithm, which is for 7 different skin diseases. Now, this is basically the training and the sampling part where we have our metrics. So on the screen, you can see, sorry, I'm just gonna adjust that. Yeah, so on the screen, you can see basically we started off with 280 images on the first instance, and we don't calculate delta as is the starting point of testing. After that, we added another 21 images, total of 1.66 delta. So along that line it goes, so just have a look. And at the end of the day, the training sample 2, was this way. This was 2 different independent samples, right? So these are 2 different independent samples. We're just trying to correlate that delta difference and pretty much bring it back together to see how much effective that our model is. So this one is the last one which we did. This one was the first sample. Then we move on to next sample. And then for verification and training, we do a AI experiment. So AI experiment is basically, you can call it as an expert opinion, dermatologist opinion. So for example, like we had collaboration with 2 institutions, especially they deal with dermatologies in around Sydney, which is one is Skin Hospital and the other one is, I forgot the name, but it comes on the slide. So this third experience was basically for those generous doctors and technicians, those actually allowed us and gave us the permission to actually take their images, feed into our model, and give them the deployed stack, and they tested it from there. So what they did was basically they went into our website and went in and basically without a new image, they put a new image in, and let's say it was melanoma, right? Most common. So they took that image, feed into a model, got the result. If they don't like it, they'd retrain it. So that's actually expert training. It's called augmented intelligence. And that intelligence actually pushed in the boundaries for the model to actually learn more. In terms of like not just us, our users also will be able to train that model in terms of whatever the images they have. But the users obviously has to be experts, right? You cannot have like those who do not understand dermatologies to train the model. So that would create bias, and obviously that would be it will be a hard time for us to basically, so there'll be circumstances will be very hard for us to move on. But yeah, so that's what it was, and they did a terrific job actually. Even they taught us a lot of things about skin cancer. This project also taught us about skin cancer a lot. So now this is a visual representation of our model, basically just a simple representation where you can see the pooling samples on the top. There, the left is our model, basically how it looks like. You can have multiple hidden layers on that. And on the right side, you can see how the images gets into converted by an autoencoder, where it basically or encodes and or decodes the image again and actually reforms the image with the certain characters that I found in the image. So that's how it looks like, right? On the left side is actually the real image. So for example, you can see there's hairs and all that pretty natural kind of thing. And then on the right side, you'll see how it actually takes in and where it learns. What is the image that actually learns? So that's on the right side. And that is an autoencoder, right? So this is a sample code where you can pretty much spin up an autoencoder. So this is that easy. But it obviously goes deeper into a dig hole, but yeah, that's pretty much a sample code for you to get started with autoencoder, what autoencoder looks like. And moving on, which is a little bit more about autoencoder. So this is a diagram which pretty much explains what autoencoder is. It has two different networks or two different types. What do you call that? You can call it two different stages. One is encoding and the other is decoding. And you'll have the image there and that'll be the reconstructed image. You come back to a little bit of an instance for you to get on. So this would be, so here on the right side, that would be an input image and that would be a reconstructed image. Right? Sorry. Now, to the main goal to learn an efficient encoding scheme for representing cases, dimensionality reduction, and intended for use for encoding schemes. To achieve this, the network is trained to discern and encapsulate the crucial features within the input image. Like I said, it basically extracts the crucial features in the image and reconstructs it, just like that, just like the other one, right? And then subsequently, it used this to learned encoding to reconstruct the image, which can then be further processed to process an output. So you might have a question where you can ask me basically is, so what makes us think that the image on the left side is exactly the representation of the image on the right side, right? That can be a question. That can be a question that it doesn't look, it totally looks different. You've got different color schemes or whatever. How can a model detect? So it's actually the features of the image which it does, and so basically it blurs it and contours it. There are 16 different image scheming that it goes through, and it reconstructs that image with, so basically I can't tell you what it learns, how it learns, but I can tell you is that this is how it detects an image and it creates that image to be, so if I send another image just like that, it pretty much reconstructs the image into this and tells us, okay, so this is actinic keratosis, this is melanoma, right? But still there are a lot of improvements to go, but this is how it works in terms of like workings of an autoencoder. And the next part is, so this is basically another representation of what the image would look like and what would be a reconstruction of an image. So basically all the three images would be the real image or the image that we actually will have, or raw data. And then when we process the image, it will look like the one that is on the below. And that's where the model actually gives you the output for. That's the image that it actually processes and gives the output. Now, so this is just a part of like what, after this, what did we find out, or what were the conclusions of it? So our systems actually diagnosed a range of common skin lesions. There are the names of it. I still cannot pronounce medical names, guys. I mean, it's so hard. I still cannot. I've done research on this. I'm continuing to do that. I've got a journal up and coming, but still hard. So it's melanocytic nevus, melanoma, actinic keratosis, and much more. Now, here's where it gets interesting. Our approach is a cocktail of smart technologies called decisional DNA, autoencoders, and neural networks. Decisional DNA is basically just an act or an impression where model actually learns through a DNA. So like humans, we have DNAs where DNA can store data. Same thing, a decisional DNA also can store data for images or whatever kind of use case you have. And autoencoders is like I explained, autoencoder basically takes an image, reduce the area, region of interest, or maybe it can also just generate one side of it if you can actually pre-program it to see. So for example, you can have a 64 by 64 image and then have an ROI set in the middle. So you need to make sure that when you do a data processing of your image, you need to make sure your images or your main concerned part of your images should be around the center, if your ROI is in the center, right? That's how it works. However, that's the best way for now, which is called Max-R-CNN. That's the extended part of this paper, which is going to get published later. And these were the collaborations that we did and had the privilege, and also I'll thank them to, they tested our product and pretty much trained it to get that accuracy and get that validation that we have. And pretty much this is the end of it. I would appreciate any questions you might have. And yeah, thank you so much. You can find me, if you are happy, if you are in need of collaboration, or you want some sort of if you're into research or publishing and stuff, you can just reach me out there, and we can pretty much go through what you have and what I have, and we can pretty much collide and do a collaboration together. More than happy to. Thank you.
Thank you so much, Kushal. Just before Kushal goes, does anyone have any questions right now?
I have 3 questions, and I ask them quickly. Number 1, why don't you use CNN instead of autoencoder?
Sorry?
CNN, convolutional neural.
So it's a type of autoencoder. It's a convolutional autoencoder. Autoencoder has different types. So this autoencoder is a convolutional autoencoder.
Okay. And number 2, you said whenever these doctors were not happy with your diagnosis.
Sorry?
You said whenever these doctors were not happy with the diagnosis, they would label it that this was not correctly diagnosed.
Yeah.
And then you would improve your system with it. You would retrain it, or you would just do a quick way to change the weights?
No, we retrain it.
With every single wrong diagnosis?
Yes, exactly. That's how it works. Because the size of images is low. That's the reason why we have enough time to actually do one by one. But if the size goes big, yes, that's where pretty much your idea comes in. Yes, we just adjust the weights and biases and pretty much return again, and should be good to go.
And one last question is that regarding the creating fake samples.
Yeah.
Use DALL-E to
DALL-E,
create.
yeah.
So you just say it based on these samples, give me another 20 fake samples of melanoma.
That's correct. It's not fake sample. We say samples. Like just generate similar
Synthetic.
images.
Synthetic, basically.
Yeah. It's like similar images, right? We just say generate. So, for example, I'll take a photo of you and I feed it and I say, generate me these kind of images. And it pretty much generates images. It's not going to be 100% correct every time. So you need to have, let's say 8 images are pretty good for you to use. You use 8. And then again, ask the model to. So that's what we did for all the 7 classifications of diseases. Yeah.
So you generated 20 synthetic ones every time.
Yes.
Maybe unevenly, like 15 non-melanoma, 8 melanoma. Again, 15 healthy skin, 7 melanoma cases.
That's correct. But in terms of we had iteration of 21 images. So 15, 9, 15, 16, 8.
16.
Like that, yeah. So that's the balance that we did, yeah. Any more?
Yeah. Sorry. Hey, right over here. Sorry.
Oh, yeah, sorry.
Great presentation. So I guess I have 2 questions. The first question I have is, in your data set, does your model predict people who have cancer or not cancer? Are there, in your data set, are there people who don't have cancer? And is your model predicting for those type of people?
Oh, that is not the purpose of.
So it was just
predict
classifying.
Cancer.
Yeah.
It's for actually to. So, for example, if you, as a person A, would have certain images, you want to know what images, what kind of disease it is, right? So our model will help you actually to input that image and get out of 7, the 7 classifications that we did.
Right.
Out
so
of 23.
Your data set had images that were based on cancer, and then you classified it.
Lesions and cancers, that's correct.
And now my second question is, well, how do you think your model would do if you fed in someone who didn't have cancer? And, would it predict or not predict those 7 cases?
So there we had error handling where we say, I didn't recognize your image. That kind of thing, the way we did about if there is an image that doesn't relate to all the 7 types of images, then it would just discard it and say, sorry, error or something.
So did the model do that, or was that?
So that's a piece of code that we do for error handling.
Okay.
Yeah, so
And
it's-
I guess my second question is
Yeah.
the architecture that you had. How did you guys come up with that architecture? Did you guys try different like poolings, different layers, or was it like something that a scheme that you had that basically kind of gave you the best architecture?
So we had this project before. We did this project before. Like I said, it started as a capstone project. So yeah.
I don't know what capstone is.
It's like I did my master's, so it was started off as a capstone project that I did for my master's,
Right.
and I went on to do the publishing and all that. But the idea about you said about architecture, right? Where did I get the
Yeah.
idea from? Is that the question? Or?
Well, the number of like the layers, the pooling, the things like that.
So there is a use case that we took that use case and we actually the model that we have
Yeah.
is so how to say this, like we already have a pre-trained, so it's like feature extraction and feature engineering, right? So when you have a model that works with images and detects the patterns on
Gotcha.
images, you just
Okay.
take that model
Gotcha.
and reiterate it and make it more advanced.
Gotcha. So you found an architecture that worked for.
Yeah, that's worked for my use case, and then it was not good enough.
Yeah.
And it was not doing the task that I did, but I retrained the model to make it a skin cancer detection model.
Very interesting. Thank you very much.
Thank you. Anything?
Awesome.
Any more?
Any more questions?
Probably the last one.
Sorry, I kind of missed. What's the latest TensorFlow feature you use for the learning?
So this one is not TensorFlow 2.13.
So what was the feature name?
Sorry,
The latest feature?
eager execution.
Okay, thank you.
So eager execution is basically if you have something wrong in your model, before we
Okay,
didn't have
probably.
that leverage to find out what was wrong in the model. Eager execution lets us to actually stop in the layer and find out what went wrong layer by layer. You get it? Okay.
Okay, we'll just take a last question.
Hi, Kushal. It was a good presentation.
Hello.
Yeah, so I just wanted to ask a question. I think in one of your samples, the delta went really high in the last value. Why was that jump there?
I can't say that, but there was a jump in the. Just give me a second.
Yeah, we can open that
So
up.
you're talking about. You're talking about the first sample training or the second?
The first sample.
Okay, the first one.
Yeah, I saw it was a very big jump from the previous value, so I wanted
Sure,
to
sure, yeah.
understand
Of course.
how that happened.
So this is the first one.
Yeah, was there a 4? I think in the last.
Is that the second?
Yeah. You see that that last value in the delta? There was a big jump
Yeah.
when you increase that number of images. Like, how did that jump happen?
So if you see on the number of images, so we have not increased much images. We just have increased 21 images, right? And the reason why I did that is because of unpredictability behavior of the model to give us the accuracy. It was really jumping high and low, high and low. So we had to figure out how to create a coefficient that can actually better predict our accuracy, how much the model is performing.
Yep.
So we had that delta thing. However, this delta accuracy that we have done 4.16, we have not taken it as a whole, but we have done an average on it. So yes, it came up as soon as the last 21 images were there,
Yep.
it came up as 4.6 delta according to the accuracy. I'm not talking about we got the stats, so that's the accuracy. But we had to put this in place because we had to give it to conclude to everyone how we did it.
Yeah.
So that's just an honest thing. But I can really say because it usually is about some sort of probability metrics in terms of you cannot. It's unpredictable how you get the accuracy, how it is done exactly to explain all of that.
Yeah. There's some
But
mathematics.
when we got that, we could not discard it, so we put it there, and when we averaged the delta, and we put it across to everyone.
Yeah, because did it affect your results in the end, or that gave you the results what you were
So
leaning
I told you
towards?
it's 40% on
Yeah.
390 images.
Yeah, that's good.
Yeah. So
Alright.
and then we added another 100 on top with our augmented intelligence, which was this slide.
Yep.
This is for the experts that came in, and then the 100 images included 460 images.
Okay, cool. And just the last note on that one was as well is how close to you are getting the output model to be very, very clear and predicting exactly as the input? Are you very
I am
close
very
to-
close, actually. I've got 75% accuracy with the use of Max RCNN. Pretty much that is going to a conference soon.
All right.
But obviously, it's currently, like, I've not finished it yet, so probably next talk.
Okay.
Yeah.
All right. I'll keep an eye on it.
Max RCNN, that's correct, sir. Yeah, Max RCNN. Average specialist? It's way low, to be honest. An average specialist actually detects, we might think that we have human error, but it's not. It's currently according to the, whatever the features, or whatever the programs that we have currently, advanced programs according in skin diseases, let's say experts and technical people are above actually than the, as per I found, as per my, even more. Even more, because they are very short. They don't have classifications. Because of AI, we give a lot of classification. We can do. So, for example, as a human, how many of a programming language you can learn at a time, right? That's the thing. So we are a little bit constructed in terms of like being full on, right? But in terms of AI, that gives us the whole leap. So we leapfrog into full capacity. Like, how many models you can, how many programming languages you can, give me. So that's the difference. But still, yes, human, basically, if you say melanoma to be exact, or actinic keratosis to be exact, so if he's an expert, he's definitely going to do better in terms of one-on-one, judgment. But then if you took all together all the classifications of all the diseases, or maybe I say 23 diseases out of that 7, then obviously model performs better than the humans. But it's really, in terms of like, it's debatable. If you talk to health practitioners, they would never get hold with this idea. Obviously, they will say, but then obviously in terms of, we get our stats, we talk stats. We don't go around find conclusion, just go and provide suggestions without anything. So according to stats, this is what I found. My model performed better than our health experts. Sorry to say, but that was true. So, yeah.
Sorry, just the last question.
What was it?
From me. Do you see this model being commercialized or used in a conversation like how Harrison and Annalise are currently doing it? If you know them?
So the Max RCNN has already been taken by UTS. For evaluation. Not this one. This is just a paper. But my journal version, which is on Max RCNN, which basically detects advanced skin disease more than detects up to 23 images, which is the 7 out of 23. So that is obviously in with developers and AI guys in UTS.
Sounds good. Thank you.
Thank you so much.
They're
Thanks,
both-
guys. Thank you so much.
Thank you. Thank you, Shal.